이거 착각하셨죠? 무전 교수님 대답 없다고 얘기했는데 네.
Oh, is there power here? Oh, it's okay. I'm not going to use this.
315.
315? Okay. And apparently the computer will go to sleep if I don't touch it. I didn't know I had that. Okay.
네, 요새 시작하겠습니다.
Good afternoon. Our next speaker is Charles Ochoa, and title is The Joy of Initial Programming. Please welcome the speaker.
All right. Hello, everybody. My name is Charles Ochoa, although I sometimes go by my middle name, Chris. And I am a data scientist employed at LogRank Analytics, which is a consulting company I founded a few years ago. And today, I'd like to talk to you about computationally hard problems. So these are problems where we don't have a good, efficient algorithm that can solve them in a reasonable time frame. But they're actually very common, so we still need to give some solution. So for example, the traveling salesman problem, that's a hard problem that I'm sure a lot of you have heard. This is the problem where a salesperson has to visit lots of cities and they want to know what is the best route they should take so that they travel the least amount of distance. There are variants on that problem for delivery vehicles, such as the vehicle routing problem. And then there are other things like how to assign tasks to workers, or even what is the best way to arrange talks at a conference such as this PyCon. And then other things like trying to figure out where you should open up a warehouse. So for those of you who know a little bit about complexity theory, these are all NP-hard or NP-complete problems. So we're not going to get a fast algorithm, but we can at least have a general framework to deal with these. And that framework is called mathematical programming. So math programming isn't this picture, and it's not writing equations on glass or anything. It's basically just optimization. And formally, I mean something like this. If we have some function called f of x, which is our cost function or our objective, that's the thing that we want to minimize. And we have some other function, this g of x, which is a constraint. Now in general, f and g can be any kind of like u-shaped function. But for this talk, I want to focus on the case when f and g are linear, and that's called linear programming. So just a quick review of what some of these terms mean. So when I say linear, I just mean that the functions are sort of a constant times a variable, and so on. So I'm sure everybody knows, but this is linear, and this is not, because you're having x multiplied by y. Now, all these variables here so far have been continuous, but you can also have variables that are integers, so like 0, 1, 2, 3, and the negatives. And in that case, you have an integer program. If you have a combination of both, you have what's called a mixed integer program. And this is actually a very mature field. It's one of the key areas of focus in operations research. I think industrial engineers cover it, computer scientists and mathematicians talk about it. So there's actually a lot of stuff out there already that will do this. But one of the points of my talk is that if you know Python, you already know enough to get started. So in Python, you have a few good options. My favorite is this package called pulp, which is for modeling the program. And that means that you use pulp to literally just set it up. And then you use what's called a solver to do the actual number crunching. And the solver can be one of many free open source ones, or like a really, really good but expensive commercial solver. So installing it is really simple. It's one line. It works on Linux, Mac, and Windows. It works in 2.7 and Python 3. And it actually is bundled with a solver. So this is the only thing you have to do to get started. So let's see a small example. So this is not a hard problem, but let's say that we want to solve this linear function subject to this linear constraint where these variables are just between 0 and 10. Just why not? So let's look at the code. If you're me and you're lazy, you have the bad habit of importing everything into the main namespace, and then you create a problem. So you use the LP problem class, you give it a name, and you tell pulp that you want to minimize or maximize. In this case, we want to minimize it. So we do that. Then the next thing is to create your variables. So here I'm doing them all one by one. There are other ways to do this that we'll see later. So each variable gets a name. You can give a lower bound and an upper bound. And then you have to tell pulp what kind of variable it is. Is it continuous? Is it integer? Or is it a binary variable? So you do that. And then the next thing to do is to set up the objective and the constraints. And pulp makes this really easy because the code looks almost identical to the equation. You literally just add it to the variable. Same thing for the constraint, but what's different about the constraint is that the constraints have inequalities. So you just add it to the variable. At this point, if you just print the problem variable, pulp gives you a nice little summary of what's going on. And this is a good way to get some intuition and to just learn, but you don't want to do this for like a real problem. If you have 10,000 variables, you're going to print at least 10,000 lines, and that's not going to look good. So solving it is very simple. You just call problem.solve, and you can check whether it worked by looking at the problem.status. And in this case, it was optimal, and the value of f of x that's optimal is 110. The values of the variables that give you that 110 you can find by iterating through them and calling .varValue, and we get this. So this was an easy problem. You could have solved this by hand. You didn't need pulp. So let's try a harder one. Right? So the knapsack problem is like actually a hard problem. And this is the situation where you have a book bag, and that book bag can only carry like 15 kilograms worth of weight. But you have all these items that you want to take. So like this item here is worth $4 to you, but it weighs 12 kilograms. This one is worth $2, it weighs 2 kilograms. The question is, which items should you take so that your book bag has the most value, but is not overweight? We can model this as an integer programming problem as follows. So let's say we have, if we look at the ith item, we can make this variable x sub I that is going to be true if we take that item and false otherwise. So with this kind of model, the total value of the book bag is basically x sub I, which is whether we take that item or not, times the value of that item, and you add it all together. And since this is just some constant times a variable and a sum, this is a linear equation, so we can use pulp. Our constraint is then basically what is the total weight of the bag, and that's going to be whether we take that item times its weight, all summed together, and it has to be an inequality. We want it to be less than this capital W, which before was 15 kilograms, and it's just whatever weight we want to carry. So let's take a look at the code now. For this talk, I've just made some fake data, and this is not very interesting. And just like before, we make a problem variable. This time I want to maximize it, so I use LP maximize. Then the next thing is to create the variables, and I do this a little differently this time. Instead of doing it one by one, I use LP variable.dix. And what this gives me actually is a dictionary of LP variable items, where the keys of the dictionary are the names of the items. So it makes it really convenient to work with it. I then add the objective, and just like before, the code is almost identical to the equation. So should we take this item or not, times the value of that item for all the items, and then summed together. And you could use a regular Python sum, but for efficiency, I'm using this function called lpsum that comes with pulp. And then you do the same for the constraint. The constraint is less than or equal to w, and you call problem.solve, and you get your result. So this was like fake data, so it's not like all that interesting. But you did just solve an NP hard problem in about 5 lines of code. So I think that's pretty cool. Let's try a harder problem. So I talked about the traveling salesman at the start of the talk. And this is when a salesman wants to visit lots of cities, and the question is, what route should he take? So how can we model this? Well, like this. Let's say we were at city I, and we want to go to city J in our optimal tour. If those two cities are connected on the optimal tour, we'll make x1, and otherwise it'll be 0. So with this kind of setup, if we calculated what the total distance traveled, it's going to be simply whether those two cities are directly connected times the distance between those two cities, added all together. And this is linear, so we're good. The next thing would be the constraints. And you might have to think about this, but we want to constrain our tour to say that you only enter a city one time and you only leave a city one time, right? If you entered a city twice, this wouldn't make sense. So this first equation says if you sum over all of the ways you could enter a given site J, that there should only be one way to enter it. And likewise, if you sum over all the ways to get out of a city, there should only be one way to exit it. And this almost works. Actually, you might get lucky and this would solve the whole problem. But in general, it probably won't. And that's because of this thing called subtours. With those equations, you might end up with this. Basically, you'll have like one cycle and then like another cycle. And we need some way to force these to just be one tour. So we have a few ways to do that. My favorite is to just try to get lucky. So basically, if we do find a subtour, then we'll go back and we'll add a constraint that gets rid of that specific one. And the constraint is pretty easy to understand. It just says that everything in this subtour should be somehow connected to everything outside of it, right? And you only want to do this when you find the subtour, because if you did it for all the subtours, that'd be way too many constraints to write. It'd be an exponential number of constraints. So let's look at the code. So just like before, I made some fake data. And if you look at this picture, it's not really like obvious what the optimal path is going to be. It's just like a bunch of random dots. So we'll create the problem using LP variable class. We want to minimize it. We'll create our variables. We'll add the objective. And then we'll add these constraints that say you only enter a city once and you leave a city once. And that's it. We just call problem.solve. We check if there are any subtours. And I'm kind of cheating. I'm using networkx just to see if there are any cycles. And if I do find a subtour, then I write that other constraint that gets rid of it, and then I just try to solve it again. So if you run this, you get something like the first time it finds 94 subtours, then 23, until you get one subtour. And one subtour would mean like the whole thing is connected, so you're done. And this was like 200 sites on a MacBook Air, and it runs in like under 5 minutes. So that's kind of, I think it's pretty good. And this is the result. So I think it's very hard to have like guessed that just by looking at the dots. So hopefully I've shown you that linear programming can solve really hard problems. But the question still remains, like, if you have a problem, how do you model it with just equations? Like, your problem might have complicated business logic, and it's not really clear how you're going to write equations for that. Well, there are some techniques. We don't have the time to go over like all the intricacies, but you can model any combinatorial problem with binary variables, and that's because we can model all of the basic logic. So we can model like an implication, an or, an and, an XOR, a not, for binary variables. And for continuous constraints, there are other techniques like the big M method, which is a way of saying, let's say I have two constraints, F and G, and I want to pick one of two of those or both. You can do that by creating a new binary variable and picking some big number M, and then just writing this equation here. And this will probably be clearer with an example. So let's take a look. So let's say you wanted to pick either x is greater than 10 or x is less than 20 as your constraint. And let's just assume that x here is bounded by 100. So since x is bounded by 100, we can make this big M value like 1,000, right? And if we just use that equation from the previous slide, we get this. And if you check it, you'll see how it works. If b is equal to 1, then we get x is greater than 10 for this equation, and x is less than or equal to 1,020. And this second one doesn't tell us anything new because we already knew x was always less than 100. So we're basically only left with one of the constraints. And then you can check for b equals 0 that works too. There's another thing we can do, which is kind of amazing. We can actually model nonlinear functions and solve them this way. But we have to be practical. What I mean here is, if you see this curve, that's not linear, but we can approximate it with these straight lines. And the math for this gets a little tricky to write down. You can look it up, but it's actually very powerful. So you can use this to model like a not straight cost function or something like that. So I think it's really interesting that these methods give you the best results without checking all of them, right? Like, how can I tell you it's the best answer when there are exponentially many answers that I should have had to have checked? And the way this works is actually really clever. And it's because solving linear equations when the variables are continuous in practice is really fast. You can use what's called the simplex algorithm. And because the integers are kind of contained within the continuous, if you solve the problem continuously, there's no way that the integer solution is going to be better, right? So some really smart people took this fact and came up with what's called the branch and bound algorithm, which is a really clever way of recursively traveling the subspace of possible solutions and getting rid of entire branches of the tree by solving the continuous problem. And I think it's a really cool search problem if you want to talk to me about it later. How am I doing on time? I got 5 minutes. Okay. So we're almost done. I'd like to go over the parts that aren't very fun. Debugging with pulp is kind of a nightmare. So I've spent hours trying to solve problems that it turns out were actually not solvable. Like, I had made a mistake where I had one constraint directly contradicting like another one, or I had problems in my data, so like there was no way for these things to sum to one. So if you're having problems, I think you should basically just check all your assumptions. Also, the form really matters here. And what I mean by that is you can have the same problem expressed with linear equations in two ways. They're both technically correct, but one way is going to be way easier for the computer to solve than the other. And unfortunately, I think it just takes experience to figure out which is the right way to do it. So you just have to get your hands dirty and try it. The other thing, it's also really hard to know what is actually hard. Like, you might have some problems that have like millions of variables and they're solved in like a minute. And then you can solve a different problem that has like 100 variables and it might take 6 hours. Or it might solve in 5 minutes for 100 variables, and when you make it 150, your computer after 6 hours hasn't returned anything. So that leads me to long running times, right? So if you do have a problem that's taking forever to solve, you can basically just be practical and say, maybe I'm okay with an answer that's like within 5 percentage points of this theoretically optimum result. And the way to do that is actually, in pulp, you can actually tell it that. So here I'm using this pulp CBC CMD. That's the solver that comes with pulp. I'm telling it to use all 8 threads of my i7 back home. And I'm telling it, stop when you get to within 5% of that theoretical value. And usually what happens is, like, if it takes 1 hour to get to 5%, it might take like 10 hours later to get to like 1%. So just stop early, and hopefully that's okay for whatever you're actually doing. There's also this thing called cuts. So you can try to add more constraints. And the reason that works is if you add more constraints, you can cut down on the size of that search space. There's a whole theory that goes into how to do this properly, but if you're stuck, just try adding constraints that like, get rid of things and see if that helps. And finally, you might just have to try other methods. So there's actually, I think, a talk next door on genetic programming. Some of those techniques can be used here. And you might just have to be really creative. What I mean by that is maybe you can solve like a small local problem and then find a way to stitch these local problems together, or you can try to spread your problem out across lots of computers, like all kinds of things. It's not that obvious like what you should do, but hopefully that doesn't happen. And I thought I was going to actually be over time, and I'm actually under. So I'm actually just going to stop here and take questions.
Thank you for speaking. And we will have some few Q&A time. So
Yes.
I'll just speak about the optimal. How do you know if the solution you've got is really optimal or at least the bound of it? Because NP-hard problems don't know if the given solution is